All right, let's get started. So we talked about a function that is delayed in time, meaning it doesn't necessarily start at 0. So let's zoom in a little bit. So that is called a translated function. Let's change to red. Do you care if it's black or red? Do you like seeing red, or do you prefer black for color? What's easier to see? What's that? Oh, so you prefer black? Yeah. The reason why I use red is because you can quickly see it on the screen, but, well, I'm just asking. I can pick any color you want. Red, black. Purple. Here are the options you have. You have red, blue, green, and yellow. That's it. Red's good? Okay, we'll stick with red then. So a translated function is, again, the one that does not start at time t equals 0. So how we handle that is exactly the same as before, right? So you're going to have our function, right? But what we're going to do is we're going to add this unit step, which essentially says it doesn't actually start until at a certain time. And if you recall, when you have a function that starts someplace over here, this right here is minus time, right? Because if a sine wave, if you look at a sine wave, that starts at 0, right? If a sine wave is up here, right, that means it's already gone through whatever the equivalent of 90 degrees of time is. So that would be plus time. So this case, if it starts over here and goes up, it's minus time. And the only reason why that works is when you look at your function, which is some sine of omega t plus that delay, right? It's whatever angle you have to put in there so that you evaluate to be sine of 0. So you can see in this case, right, if I plug in t equals 0 there, the only way to get the peak is when theta is equal to 90 degrees. If I plug in and get that time to start at 0 there, the only way that way works is if it's negative time. Okay? So anything that starts after time t equals 0 is actually considered negative time. Does that make sense? It's kind of always confusing because it goes backwards for what we're typically thinking of, but it's actually backward in time. So what we're going to do is we're going to do our integral here, which is our f of s. And now, whoops, I went too far down. And you'll notice the normal expression starts at 0 to infinity, right? Because it's a unilateral Laplace transform. But the problem here is that I'm integrating with respect to dt, and my functions are delayed in time a little bit. So what I'm going to do is I'm going to introduce a new variable called tau, and it's not my time constant, it's just a new time variable. And that's going to be the same thing as t minus a. And so what I have now, if time is 0 here, right, our lower limit becomes negative a or alpha. Our upper limit is still infinity minus a, which is still infinity. And so now I'm integrating with respect to tau's here, okay? I'm no longer integrating with respect to a's, all right? See how that's done? So this is e to the minus st, so t is equal to tau plus a is what I'm saying. So that gets substituted into that. That's the only t value that we have that we can't substitute in. All right? And when we do that, our expression now just becomes f of tau, u of tau, e to the minus s times t plus alpha. Well, I'm differentiating now with respect to tau, right? Not s. So this is just a constant, isn't it? I can factor out e to the minus a times s and completely factor that out of the integral because it doesn't vary with respect to time. Okay? So what that means is this is now my integral multiplied by that constant, which is just my function converted or transformed into the Laplace domain multiplied by e to the minus as. So here's the thing. if you have a time domain function that is delayed by a certain amount of time, how do you go to the Laplace domain? You take the original function and assume it was never delayed at all, and you just bring that to the time domain. So sine of omega t, e to the minus 3t, whatever it is. And then you just bring that to the time domain, the Laplace domain. Then you multiply it by e raised to the negative a times s, and your delay is the a term. All right? That's all you need to do. Just treat the original function, bring it to the Laplace domain, do e to the minus as, and you're good to go. All right? Questions on that? That becomes more important when you do Bode plots, because when you look at frequency response and you're looking at how things get shifted in time, if you have higher frequencies, right, time gets to be a big deal. So when you're looking at things being out of phase, when you include this phase shifting element in here, you can have some problems. Okay? Questions on that? All right? So you can also do the same thing, which is you multiply a time domain function by e to the t. It's just the same thing as taking that Laplace domain variable s and adding an a term to it. All right, so I had this set up earlier, but then I had problems. So let me go ahead and show you the wonder of technology. And let's see if I can make this work by adding in a file. It connects. It connects really quickly. This probably is not being recorded at this point, but yeah, it is recorded. Huh, why won't it zoom in? There we go. Apologize for the quality. It was much better earlier. It's not great quality now. So let's add on another slide. And let's do a search this way, because that's essentially what I did. Gotta love technology. That one's not very good quality, so let's go back. Let's see. Just trying to find good quality. Here we go. It's not in English, but it's okay. So this is actually in your book, right? We'll figure it out, right? It says impulse function, and then it says unit step. Those are the first two. So what it shows you, once you get to the point where you're comfortable using the f of t, integral of f of t e to the minus st dt, and you're getting comfortable doing that process, you actually don't need to do that every time. You can just look at your Laplace table and immediately just say, well, what does my function look like? Does it look like e to the minus alpha t? Because if it does, then I can just go ahead directly into the Laplace domain without having to do all that integration and get f of s. All right? So any of these functions here, any single function, there we go, okay. Any single function there, you just have to make it look like the table. So use the variables that you have, and then you can go ahead and make it work. That's all it is, all right? So sine, I believe. I don't know what language this is, but like I said, it was working fine earlier. What's that? Spanish, Spanish? Could be, I don't know. So this is actually sine of omega t. So anytime you see a sine of omega t, figure out what omega is, and then you can immediately go into the Laplace domain just by going omega over s squared plus omega squared. And it's better off to leave it as omega over s squared plus omega squared, mainly because if you leave it as the omega squared, it actually tells you what the omega term is, because when you do partial fraction expansion going back, you need to know what that omega term is. So oftentimes if you have sine of 3t, so sine of 3t, let's scroll up. Sine of 3t, if I look at my table, right, my table says sine of omega t converts to Laplace as omega over s squared plus omega squared. So I can immediately see that omega equals 3. So my f of s function, which is the Laplace transform of sine of 3t, is just going to be equal to 3 over s squared plus 3 squared. It's better to write it as 3 squared instead of 9 because it's going to make it a lot easier for you in terms of figuring out what's in the table. Okay? Far, far, far easier for you to do that. And oftentimes, you actually, like I said, have to go back and do partial fraction expansion. Sometimes you'll have a case where you have 1 over s squared plus 9. Does that look like the table? Doesn't, does it? But does this look like the table? Whoops. Same value, right? Can I go right back to the Laplace domain and can I say that this is just equal to sine of 3t? No, I cannot because I have a 1 here. What do I need up there? A 3. So here's a trick. I'm going to put the 1 up here. I need a 3 or omega up there. So I multiplied the equation by 3, but I can't just multiply something by 3. What do I have to do to make sure it stays in equality? Divide it by 3, right? So if I multiply by 3, I have to divide. So this is 1/3 sine of 3t, right? Because multiplying a constant by the time, a constant in the time domain is the same as multiplying by that exact same constant in the Laplace domain. So sine of 3t, which is 3 over s squared plus 3 squared, is close, but I need 1/3 of that to actually get this equation to work out properly. So that's a lot of what you're doing with the tables is just massaging the tables to do that. So multiplying by constants is one way, dividing by constants is a way, and then we'll do partial fraction expansion. So let's add a slide here. And do the video. And I don't need these because I've got those. Now we should be back to where we were. Let me zoom in a little bit. Okay, so first thing we're going to do is we're going to sort of do these transform functions to figure out derivatives and integrals and kind of see what happens, right? Because the whole thing about algebraic, we want to take our differential equations and convert them to algebraic equations. So we have to figure out what derivatives and integrals look like in the Laplace domain. Hopefully they look like multiplication and division. Otherwise, there's not much purpose to it. So the first thing we're going to do is take the Laplace transform of a derivative of a function. Should be able to do that, right? Shouldn't make a difference. So all we do now is we plug it into our equation, f of t e to the minus st dt. So we get that here. Okay? So we have a function that is a derivative, right, of a time domain function, e to the minus st dt. So we can't figure out how to take the integral of this because we have two time domain functions or two time-based functions that are making it very difficult for us to integrate. So usually you would do integration by parts, right? Remember that from 127? And integration by parts, the usual way that you do it is you take the easiest part to differentiate. In this case, it's e to the minus st. And then the rest, let that be dv. Okay? So if you don't recall integration by parts, the integral of u dv is equal to uv. So that original u value, then you integrated out your dv to get v, minus the v du. So you're integrating, now that this is the actual term you're going to integrate with those limits. So if I pick u to be equal to e to the minus st, so this part right here is u. My dv has to be the rest, so it's dft dt. Actually, I'm missing my dt, which should be here, so sorry about that. Let me show that again. So this is e to the minus st dt. No, sorry. It's the other one. It should be here. dft dt divided by dt. So I did have it right. I'm just saying it's df dt, and you'll notice here that this term and this term will cancel. So it cancels it out. Sorry about that. So u equals e to the minus st, and dv equals the first derivative of my function. Now I'm going to take the derivative of u. So the derivative of that with respect to time is negative s e to the minus st. And when I integrate my dv, I just end up with my original function, my f of t, not integrated. So I'm going to substitute that into here. So that's my original function. Now I'm going to do my uv. So this is my u. This is my v, evaluated from 0 to infinity. And then I subtract from it my integral of v du. So this here is v, and this is my du. Okay? If I look at this is very touchy, so one of the problems with this program is you can't go backwards, so if you do, it erases, yeah, it erases what you don't want. So let me turn, it's not easy to append, so I apologize. Okay, so we are
5.3.
Yeah, the bottom of page 9, right? Okay.
Nope, we were up one more.
Could you zoom in a little bit, please?
This is 5.3, right? The bottom of page 9?
Yep.
Okay. There. All right. Hopefully we won't have technology issues. So let's go back to it. So again, here is my term. So here is est, f of t, evaluated from 0 to infinity, right? So that's my value of t. And then here is my integral, 0 to infinity, f of t, s e to the minus st dt. So let's go back and look at e to the minus st, f of t, evaluated from 0 to infinity. We're going to plug in infinity. So we have e to the minus s times infinity times f of infinity. Whoops, it's an ugly looking infinity. Let's try that again. Right, that's the upper integration limit. Then we're going to subtract e to the minus s times 0 times f of 0, right? Because we're just substituting in t equals infinity and t equals 0. So e to the minus s times infinity, what does that equal to? What is anything raised to the infinity power equal to? Regardless if it's multiplied by s or k or t. E to the infinity is always positive infinity, right? If I 1 over that, I'm going to get 0. So 0 times f at infinity, it's always going to be 0. So that term cancels out. This term right here, what is e to the minus s times 0 equal to? 1, isn't it? E to the 0 is 1 times f of 0, correct? So it's negative f of 0. So when you do your Laplace, you have to subtract, when you take the derivative, your initial condition out of there. Right? That's the first thing we need to do. Now let's look at, try it. Well, hopefully we didn't override it. We'll see. So, got to be very careful. So now my integral of 0 to infinity f of t s e to the minus st dt is what I need to integrate, correct? That's what's remaining. Is s getting integrated at all here? My integrating variable is t, right? It's dt. So this is going to be equal to 0 to infinity. S just gets pulled out front. F of t e to the minus st dt, right? Isn't this the definition of f of s? Isn't it the original function f of t e to the minus st dt? Isn't that the definition of f of s? Way back at the beginning, that is the definition of how you do the Laplace transform. So, the derivative of some function with respect to time gets converted into the Laplace domain by multiplying that function that you're taking the derivative of, whatever that function is. You're multiplying it by s. So convert that time domain function to the Laplace domain, f of s, and then you multiply that by s. So it's s f of s minus your initial condition. And hopefully this is clear. I'll try to make it a little more clear. This is a capital F. This is a lowercase f. This is a time domain. This is a Laplace domain. Whoa, that's a good thing, isn't it? Because we already said we don't want to solve differential equations. We want to solve algebraic equations. So we just saw how by converting or taking the derivative of something in the time domain is exactly the same as multiplying the Laplace domain function, or converted function, f of s, and multiplying it by s. So all we need to do is every time we see a derivative, multiply it by s. That's step one. We don't take derivatives in the Laplace domain, almost always. There's a couple cases you do, but the vast majority of the time, you do not take derivatives. Okay? Pausing to make sure everybody is following along, because it's a pretty important topic to note, because again, that's the whole reason why we do Laplace, is so we don't have to take derivatives.
Could you just go over that one more time?
The text or the actual write-up?
What you were just saying, like Laplace. So we don't take the.
So in the time domain, we live in the time domain, and we live in a world where we have to take derivatives and integrals, right? Speed, position, all those stuff, you're doing derivatives or integrals all the time, constantly to get there. In the Laplace domain, we don't actually take derivatives and integrals. We just want to do algebraic equations, which is multiplying by something, dividing by something, adding or subtracting. So what we do is we take these time domain functions, these f of t's, that have derivatives that you have to take and integrals, and we convert them to the Laplace domain, because as we just saw in the case of the derivative, you don't actually have to take the derivative, you just multiply by s. And that's the same exact thing as multiplying in the Laplace domain by s. So I don't actually have to do a derivative, I just multiply by s. And so any of the work that I need to do to solve a differential equation, I just do in the Laplace domain, because I just solve my algebraic equation. Okay?
Thank you.
Sure. Let's do integral. So now we're going to integrate f of t. And we should, right? We should get no longer an integral, but something that's algebraic. So we have to, again, do the integration by parts. So here is our, let me move this out of the way first, because it's, so I get this out of the way, and it won't go. Here we go. No. Don't know how, there we go. I get that one out of the way. I don't know exactly where. Let me try this. Let's see it this way. Well, that didn't work. Okay, let's get this out of here. Yeah, you can tell I'm not a technology.
Do what you just did. You selected it.
So I got it selected. Ungroup it. I didn't think it was grouped, but I can try. Now somehow I'd like to copy and move it out of there, but it doesn't want to seem to do that. So, oh, there we go. It worked. I don't know what I did. Let's not.
So I try to remember.
Right. Okay. So we want to go ahead and integrate. So we're going to take the integral of a function f of t, and you're going to do the Laplace transform. And just like we did before, we're going to stuff that in for our function. So it's the integral of f of t, e to the minus st dt, and we have to evaluate it from 0 to infinity. We're going to do integration by parts. So our u is going to be our integral. Our du is here. dv, you can take a look at that. We're going to substitute that and have our expression here. So now we have an integral, so let's specify that. So we have the integral f of t dt e to the minus st evaluated from 0 to infinity. Why is it two integrals? Because I have to, my f of t is an integral.
Oh, okay.
Right? I'm looking at this guy, so I actually have two integrals there. So if I focus on this one, right, I have the integral of f of t, so this is f of t, sorry, dt, e to the minus infinity, right, minus the integral 0, whoops, not that infinity, let's erase that, minus the integral f of t dt e to the minus 0. So essentially, this term here gets substituted as a 0. So I end up with my f of 0 term, my initial condition divided by s. This expression over here, let's bring that up over here, and we have 0 to infinity e to the minus st f of t dt. I'm going to pull the 1 over s out of there, put it out front, just like we did before when we multiplied it by s. And isn't this our f of s equation from back at the beginning?
S is just some constant.
S is a variable, yeah. It's a complex representation of frequency. It's just j omega. So it's not changing. So when I integrate with respect to t, it's just a constant. So my integral, I just take my function, my original function, whatever it is, I convert it to the Laplace domain, and I divide it by s. So to summarize, if I have a derivative of a function, you take the Laplace domain, you multiply it by s. Technically, you should subtract the initial condition, but we almost always assume that it's going to be no initial conditions. They're going to be 0, so we almost always ignore them. If we want to integrate f of t, that's the same thing as going to the Laplace domain and dividing by s. And that's it. There's no more differential equations, is there? There's no more derivatives. There's no more integrals. What other parts of differential equations do you need to do? There's none. So if we can convert those time domain functions to the Laplace domain, you don't have to solve differential equations. And that's what engineers do. Don't solve differential equations unless you have to, if you're in 258. Okay? Oh, it's all. I'm going to go ahead and add a page because it's ungrouped it all, so I got to make sure it moves all at once. Jesus, sorry about that. It's like it's.
Oh, there's the back arrow. It's down at the bottom of the page.
What's that?
See how it says 6 out of 6?
Yeah, I know, but I don't know why it's automatically incrementing it. It's just, it's like it's very touchy.
I think you can hit the back arrow and it goes back a page.
If I do, I'm just worried it's going to overwrite the audio. So let me just go ahead and insert the file. And then it should all be together. We're all back together again. Okay? One of the things that you can do is something called the initial value theorem. So I sort of gave you a little bit of an introduction to this at the last class, how I said you can do a lot of things in the Laplace domain, so you don't have to solve back for the time domain. One of them is called the initial value theorem. Initial value theorem basically says what is f of 0 in the time domain. You can get that value by, if you take the derivative, right? The derivative of this function is f of s minus f0, which is equal to here. My f of s0 is my s f of s minus this term here. If I allow s to approach infinity, right? So if s approaches infinity here, then that term goes away. So f of 0 is equal to s f of s, right? So the final value theorem is if I do a limit as s approaches infinity, all I need to do is go s f of s. So whatever my value of my function is, whatever my s is, I allow s to approach infinity, and I actually have my initial condition. What do you think the final value theorem is? What does that equal? It's the same thing, but you allow it in the opposite direction. So you'll do initial value and final value theorem a fair amount next semester. Again, when we're trying to solve for things by staying in the Laplace domain. Okay? So that's sort of a harbinger for next semester, but just a little bit of a teaser in terms of doing that. Okay. So here's the downside of this semester is we don't have all those tools that are super helpful, or maybe we're looking for a response. So if we have a voltage that energizes a circuit or a system and we want to see how that circuit or system responds to the voltage, we actually want to see a time domain function, so how it's varying, as opposed to just a particular value. So we're going to actually have to go back and do everything into the time domain. So we have to go from our f of s and go to f of t. And the way that we do that is by partial fraction expansion, mainly because, do you recall f1 of s plus f2 of s does equal f1 of t plus f2 of t. But what is not the case, f1 of s times f2 of s does not equal f1 of t times f2 of t. Multiplication in the time domain is not the same as multiplication in the Laplace domain, so we can't do that. But the first one, by adding functions together, we can absolutely do that. That works perfectly fine. So we're going to go ahead and add those functions together to go ahead and do that, which means we have to do a lot of partial fraction expansion unless we can make things look exactly like the table. Okay? So those tables that we were looking at before, and you can bring these up, and I don't know a way to put these on the side with the slides, unless I insert it every time. But you're going to go ahead and do that. So we'll do partial fraction expansion. And the generic way to do it is if you have a function which has a numerator and a denominator, you can break that out into individual functions by, this should be A1, A2, A3, A4, just on and on and on, adding the constants. These right here, does anybody know what the alpha 1 and alpha 2 are equal to? Those are the poles or zeros or roots, depending on who you ask. So it's the root. So if you have a denominator which has a function of s, it could be s cubed plus 7s plus 6s plus whatever. You can actually break that down into the 3 roots, right? Because it's s cubed, you know it has three roots. So whatever the, I'm not sure why it's so touchy. So our denominator of s is going to have some s raised to the n power. This here has a to the n coefficients, okay? When you do partial fraction expansion, however many n you have here means however many coefficients you have to pull out of there, all right? And you write each of these as the negative of the root, okay? So if I have a simple one which is s squared plus 7s plus 12, that's in my denominator. How would I do partial fraction expansion of that? Let's say it's 3. Three over s squared plus 7s plus 12. I want to do partial fraction expansion, right? That does not look like the table. So I know it has to have some s plus a plus some s plus b, right? What's the easiest way to go from this to breaking it up into separate terms? Factoring. Quadratic equation, right? If it's a second order system like this, negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Did I go too fast? Should I spell that out? Quadratic equation? Who here doesn't remember the format? Don't be shy. Everybody remembers it? One person, one's honest. Quadratic equation. If you have an equation that has as squared plus bs plus c, you can solve for the roots of that equation by going negative b plus or minus the square root of b squared minus 4ac all over 2a. That's the quadratic equation that you probably learned in algebra 2, maybe. So it might be a while since you were exposed to it. That's the quadratic equation. So in our case, you can see that this a is equal to 1, b is equal to 7, and c is equal to 12, right? So negative b, 7, plus or minus the square root of b squared, 7 times 7 is 49, minus 4ac, 4 times 1 is 4, times 12 is 48, all over 2 times a, which is 1, gives me that. So this is equal to negative 7, plus or minus, what's the square root of 1 equal to? 1, all over 2, which is equal to negative 7 plus 1 over 2 is the first root, and negative 7 minus 1 over 2 is the other one. So that's going to be equal to negative 6 halves, or negative 3, and negative 8 halves, or negative 4. So in this case, this becomes s, and you can take minus the root, plus 3, plus s plus 4. If you multiply and you do a FOIL of s plus 3 and s plus 4, do you end up with s squared plus 7s plus 12? Sure do, right? The only thing is, what are your coefficients to get a 3 up there? That's the part that you may not have been exposed to, right? Because when you multiply all this stuff out, you should end up with this original equation, shouldn't you? So we've got this part taken care of. What we don't have is that part. I don't think it's going to be a 3 and a 1.
Oh, it's plus. Is it plus or multiplication?
Plus.
Oh, it's 2.
So we know that we have, so let's rewrite this. So we have 3 over s squared plus 7s plus 12 has to be equal to something over s plus 3 plus something over s plus 4, right? Let's just arbitrarily call it a and b, and we'll solve for a and b. So for those of you who have taken differential equations, you've seen ways to solve for a and b. This is a way that we'll teach it in this class, and I encourage you to try it. It works exceedingly effectively in this class. So how do we solve for a? Well, what if we multiply both sides by whatever is under a? So 3 times s plus 3. And I'm going to go ahead and put the terms in the denominator as factored out. S plus 3 times s plus 4 equals a times s plus 3 times s plus 3 plus b times s plus 3 over s plus 4. Have I done anything sneaky or snarky? I just multiplied both sides by s plus 3.
And then you do the same thing with the b.
Well, I'm multiplying both sides, which means I have to multiply both sides, which includes the b term, by s plus 3.
Do the s plus 4.
Yes, yep, you're skipping ahead, but that's okay. So we have s plus 3. Let's do a little bit of math and factor that out. So we have 3 over s plus 4 equals a plus b times s plus 3 over s plus 4. Okay, just some math. This is a linear system, right? A linear equation. A linear system says for any value that I plug in, any value of s that I plug in, if I get a correct value or a result, then that value is going to work for any number. So what if I evaluate this entire equation at s equals minus 3? Whatever value for b I determine, or a I determine, it's going to be correct. Well, by picking s equals minus 3, doesn't that equal 0? So a is going to be equal to 3 over s plus 4 evaluated at s equals minus 3, which is 3 over 1, which is equal to 3. Questions on that one? And as Liam said earlier, to solve for b, we're going to multiply both sides by whatever is under the b term. So 3 times s plus 4 over s plus 3 times s plus 4 equals a times s plus 4 over s plus 3 plus b times s plus 4 over s plus 4. Factor when I can, and I'm left with 3 over s plus 3 equals a times s plus 4 over s plus 3 plus b. I can evaluate it at any value of s I want. I'm going to evaluate it at s equals minus 4. Why? Because that term is multiplying by 0, doesn't it? When s plus 4 gets evaluated at s equals minus 4, what happens? It goes to 0. So what I'm left with is b equals 3 over negative 4 plus 3 equals minus 3. So my original function, which was 3 over s squared plus 7s plus 12, equals 3 over s plus 3 minus 3 over s plus 4. Buy that for $1? Let's check. Shall we check our work? Let's check it. How do we check our work then? Common denominator and put them back under that same common denominator and multiply it out. So this is equal to 3 times s plus 4 minus 3 times s plus 3 all over s plus 3 times s plus 4, right? So I have 3s plus 12 minus 3s minus 9. Now I got to FOIL it. S squared plus 3s plus 4s plus 12 equals, the 3s's will cancel. 12 minus 9 is 3 over s squared. 3s and 4s is plus 7s plus 12. Does that equal that? Sure does. So this method works. In your classes when you were taught how to do partial fraction expansion, were you taught basically the matrix approach where you try to line up A, B's, and C's and do it that way? That's one way to do it, and that works fine. I like doing this way too because there's less math. Like when you collect terms and do all that stuff, you can make lots and lots of math mistakes.
Also, it's logical.
Yep.
You can easily follow it.
And this method will work no matter what the root is. We have to do a tweak here and there to make it work for us. And we'll show you how to do that as we get more complicated. So let's zoom. Oops. Let's get those out of here. There we go. Here's another one. 3s plus 7. I'm going to sit down because I can write a little neater. 3s plus 7 over s squared plus 5s plus 6. Do you want to write it out, or do you want to just use the what's in the notes? Notes or write it out? Your choice. Write it out? Okay. So the first thing we're going to do is quadratic equation, because s squared plus 5s plus 6, we don't even know if it looks like the table or not. So anytime you have something that's got something raised to a power other than 1 in the denominator, the very first thing you should do is try to factor it down to its simplest form. So we're going to do the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Negative 5 plus or minus 1 over 2, which is going to be equal to negative 2 and negative 3. Right? I did that quadratic equation slightly faster, but does anybody need me to go slower to do that, or does that make sense? Good? Okay. So now I'm going to set up my f of s is going to be equal to s plus 2, s plus 3. So I'm taking the negative of the roots there. This is a over s plus 2 and b over s plus 3. So now I'm ready to solve for a. So 3s plus 7 over s squared. Whoops, not s squared. Let me put the factored forms in here. S plus 2 times s plus 3 equals a times s plus 2. So whatever is under the a term, I'm going to multiply both sides by that.
Didn't you need to carry that s plus 2 along to the 3s plus 7?
Yeah, I'll do it on the other side in a second. But you're right. So I've got both sides multiplied. Now I'm going to cancel out the s plus 2's. So 3s plus 7 over s plus 3 equals a plus b times s plus 2 over s plus 3. I'd sure like to get rid of my b term. Is there a number that I can substitute for s that makes getting rid of b pretty simple?
Negative 2.
Yeah, if I evaluate this linear expression at minus 2, then the b term goes away, right? So A is going to be equal to 3 times negative 2 plus 7 over negative 2 plus 3. So I have 1 over 1. A is equal to 1. Got that one? Ready to go on to B, or do we want to pause here for a little longer? All right, if we're good with that, let's do B. So 3s plus 7. I'm now multiplying both sides by whatever is under the B term. S plus 3 over S plus 2 times S plus 3 is equal to A times S plus 3 over S plus 2 plus B times S plus 3 over S plus 3. Again, just multiplying by whatever is under the B term. Cancel out my S plus 3's. I have 3S plus 7 over S plus 2 is equal to A times S plus 3 over S plus 2 plus B. Is there anything I can multiply to get rid of the A term? Yeah, if I evaluate at S equal to negative 3, I'm going to get rid of my B term. So let's move that up. So B is going to be equal to 3 times negative 3 plus 7 over negative 3 plus 2. So negative 9 plus 7 is negative 2 divided by negative 1 is a positive 2. So my original function, which is 3s plus 7 over s squared plus 5s plus 6 is going to be equal to 1 over s plus 2 plus 2 over s plus 3. Those are the same. And if you want to multiply those out, you can. Do we need to multiply those out, or do you feel pretty comfortable that these are correct? Anybody need to multiply them out, or? All right. So now, this is my f of s, right? These are all equal to each other. So I can do the inverse Laplace transform of 1 over s plus 2 over s plus 3, right? And if you remember from your Laplace table, e to the minus alpha t is the same thing as 1 over s plus alpha. So f of t is equal to e to the minus 2t, right? Because that's the same, right? The alpha there is the same. So e to the minus 2t plus e to the minus 3t, right? Because this alpha here and here, they're the same. The problem is, what do I do with the 2? Do you remember in the Laplace domain?
Would it be like 2e to the minus 3t?
Yeah, so multiplying by a constant in the Laplace domain is the same thing as multiplying by that exact same constant in the time domain. So this is that. And if you get confused, you can always do this. Minus 1 s plus 2 plus 2 times the inverse Laplace of 1 over s plus 3. So until you get more comfortable and more proficient with solving for doing inverse Laplace transforms, you can just simply crank through and do a bunch of these numbers. Move things around to make it easier for you to see. So, as I said, the differential equation that is represented by this here ends up with a solution like this. And this circuit or system here could just be an RLC circuit. Is what you could have there, depending on what you're looking for, voltage or current or whatever. It could just be an RLC circuit that you're looking for a waveform response. All right, questions on that? The capital F here, that means it's in the Laplace domain. So if you look for capitalize, if it's a capitalized function, that means it's Laplace. If it's lowercase, that means it's the time domain.
So what type of equation, like you were saying it's an RLC circuit, so what would be an example of a circuit that would use that type of equation?
Type of equation,
Would use that equation, like that, for instance.
this equation here,
The, yeah, or the one that we just made.
the f of t.
Yeah, that one.
So it could be, I have a DC circuit with an R, an L, and a C. And this would be an overdamped system whose response would look like this. If you're trying to figure out, let's say you're trying to figure out the current through here, it would be something that does this. It'd have these two exponents added together. That would give you a result that looks like this. So an overdamped system would respond this way. Two exponentials, actually they're decaying exponentials, so they would actually go this way, most likely, because it's e to the minus 3t. So something like that would be how it's represented. So any second order system, anytime you have two energy storage devices, you could do that. For those of you who worked in the process control world, what if I'm filling up a tank, and the filling up of the tank is based on the level that I see here. So I'm trying to maintain a certain level. So this tank here has it's usually modeled as what's called a first order process. So this would have some sort of a f of t here. Then the level of the tank is going to a PI, or proportional plus integral controller. And the two of these combined together would give you a response that looks like that, depending how you tune it. So if you did tuning where you were looking for overdamped systems, you don't mind if the system is really slow, you'd end up with a system that responds like that. So any physical system, most physical systems in and of themselves, you represent them just basically as a first order process, right? A car speeding up. That's just, you get up to a certain speed and then you get to that speed. You're not ringing back and forth to get to that speed, right? Unless you're jumping on the accelerator back and forth. But many real-world processes are first-order systems. It's only they get second and higher-order systems when we start adding things in there. So that tank level maybe gets more complicated if we start pumping water into it, or we pressurize the tank, or we start mixing chemicals into it and we're trying to control different things. Then we complicate it because we're not just maintaining tank level, we're maintaining temperature or chemical consistency and whatnot. And so that's where this class has a lot of cool aspects of it, because it's just, it doesn't matter the discipline, all these techniques, these analysis techniques apply. Okay? So does that answer your question? Sort of? Liam? Okay. So you can check, this is what we had, and then when we multiply it out, we've got it here. Ready to do another one? Another one, yes? Do you want to just follow along in the notes, or you want to write it out? Is it more helpful to write it out, or? More helpful to write it out? All right, so we have f of s is equal to 5s plus 40 over s squared plus 4s plus 29. Again, I have a function in here that first thing I want to do is I want to bring that to a lower order function, so I have to do the quadratic equation. So negative b plus or minus the square root of b squared minus 4ac all over 2a, which is negative 4 plus or minus the square root of, I have a negative 100 in here, right? Whoops. We got a square root of a negative number. It's time to call it a day, right? Except we're electrical engineers. We deal with square roots of negative numbers all the time. Isn't this just equal to, right? Isn't that the same thing? Which is equal to negative 4 plus or minus, what's the square root of 100? 10. What's the square root of negative 1? J. which is equal to negative 2 plus or minus 5j. Okay? So here's the thing. This is not what it appears, right? This is a real part and an imaginary part. It's best to write it this way. S minus the real part, that quantity squared, plus the square of the imaginary part. Okay? And the reason why we do that is because it's going to look very close to your table. So in this case, we're going to go ahead and we're going to bring that back and we're going to say that's equal to S minus the real part, so it's S minus 4, or plus 4 I should say, quantity squared, plus 5 squareds in the denominator. Okay? If you look in the table, there's one that has the form of S plus alpha over S plus alpha squared plus omega squared. And there's another one that has omega over S plus alpha squared plus omega squared. This one, I believe, is the cosine of omega t e to the minus alpha t. And this one is the sine of omega t e to the minus alpha t. So all I need to do is make it look like the table. Well, I've got 5s plus 40 here, right? This one says I need s plus 4, right? I have 5s plus 40. Isn't that 5 times s plus 8? Right? Which is equal to 5 times s plus 4 over that denominator. What did I do with the rest of the 4? I still need to keep it. So plus 5 times 4 over the denominator. So this has a 5 out front, and then plus 4 over s plus 4 squared plus 5 squared. See how I broke those out? I just factored out the 5 right here, and then I have s plus 8. So I've got an s plus 4 and a remainder 4, so I just pulled that out to the other side. And then let me just make sure that I'm remembering this correctly. Oh no, I did it incorrectly, so I apologize. This is supposed to be s plus 2. So this should be 2. Oops. Not 4. Oh, how come I won't erase that? It's odd. That should be s plus 2. So let me erase this here and make that a 2. So I put the 4 in there. It should have been 2, so I squared it. So this should be s plus 2. Try that again. S plus 2, so I need an s plus 2 squared. So I have 5 times s plus 2, so I have s plus 2 over that denominator, which means I have 6 left. So I have 5 times 6 over that denominator. So this one's good to go, right? I have the s plus 2 up here. So that's good. I've got that one. Now I have a 6 and a 5 over here. I need to have a 5 up here, right? But I have 5 times 6. So what do I need to do? Just pull the 6 over here, right? So what I have now is the inverse Laplace transform of my original function, which was s squared plus 4s plus 29, and it was 5s plus 40, correct? Is going to be equal to 5, no idea why it just does it every once in a while, 5 times s plus 2 over s plus 2, that quantity squared, plus 5 squared plus 6 times 5 over s plus 2, that quantity squared, plus 5 squared, and I take the inverse Laplace transform of that. Okay?
What's the reason for putting the 6 out front and the 5 where it's at?
Because if you remember from the table, the expression it has omega over s plus alpha squared plus omega squared. I can only have omega up here. If I have more than omega, I have to put it out front. I need 5 there, but I actually have 30, so I'm just factoring out the 6 to make it work. So this is going to be equal to 5 e to the minus 2t cosine of 5t plus 6 e to the minus 2t sine of 5t. Let me just make sure I didn't get my sines and cosines backwards. Nope, I got them right. That's your expression. So in this case, did I have to do any partial fraction expansion? I did not, right? I ended up getting no partial fraction expansion. But what I needed to do was I needed to set this up into the table to make it work for me. Otherwise, I just couldn't get it. I couldn't make it work from there. So by actually just doing the quadratic equation and then making it look like the table, then I just needed to massage the numbers to separate them. So not partial fraction expansion, because I actually didn't break the denominator up into 2 separate terms. I just needed to pull out the extras and make it look like the table. So sometimes you have to do partial fraction expansion. Sometimes, like in this case, you just had to do a little bit of slogging to get there. And that's the problem with Laplace. I just said it, slogging. A lot of algebra, isn't there? Whole lot of math. That's the unfortunate, part about why Laplace isn't the end-all be-all, because you can see how much algebra I needed to do to get the answers to look right. But as I said, in 325, what you'll end up doing is you'll live mainly in the Laplace domain. You won't have to go back into the time domain. So the initial value theorem, the final value theorem, there's some Bode plot analysis, Routh-Hurwitz, root locus, all that stuff. You'll actually stay in the Laplace domain to make your life easier.
So it's really just the transient stuff that you need to go back and forth.
It's when you need a waveform, when you need to see how the waveform responds. And so when you look at MATLAB has a software application called Simulink. That's what essentially it does. It does all this inverse Laplace transforms and does everything in the time domain for you. Actually, it might even just not even convert things to the Laplace domain, because if you're a computer and you can solve differential equations quickly, why would you even do the conversion? But as us as engineers, right, we just aren't mathematicians that like to do differential equations, so we struggle with that. All right, should we try to do this one last example? I've got 5 more minutes, or should we call it a day? Who wants to stay? All right, so this one I'll just do it quickly because we don't have a lot of time, so I won't keep you over. So this one has 2 functions. Those clearly are multiplied, right? So we know that it has to have s squared plus 4, and this is going to be s plus 4. Anytime you have multiplying something in the s other than 1, you need to factor it out, okay? Because if you remember, it's e to the minus alpha t is s plus alpha. That has to be a 1 out front of there, so you have to factor out a 2. So the first thing you do is factor out a 2, and you have 10s over s squared plus 4 times s plus 4, okay? Then you can do the quadratic equation if you need to, but you actually don't need to. You'll end up with this expression. So we're going to do it just this class. We're going to have, we'll separate them all the way down. We have a, b, and c for all the roots. We solve for a, b, and c just like we normally do. And you can see that a is going to be a complex number. B is also a complex number, and c is a real number. Here's our expression here. Now, what we do, though, is these 2 terms, they're going to have e to the minus 2jt, right, when you go back into the time domain. Does e to the minus 2jt exist in the real world? It does not. So what you want to do is you want to combine them into this s squared plus 4, because that's just going to be s squared plus 2 squared, which is something that looks like the cosine or the sine of some omega t. So by combining them here, right, by doing all this work and combining them, I now end up with an expression that's 2s plus 2 over s squared plus 4. If I continue on, and then just break them up, right, because I have a 2s over here, I can just break them up. I have 2s over s squared plus 4 plus 2 minus 2. Whoops. Not sure why that happened. Now I can just take these individual terms back into the Laplace domain. Okay? And so for the next class, we'll look at another way, which is this as plus b, which is what you were taught. We probably won't do that one because it's more difficult. We'll use a third way, which has to do one substitution or approximation, but makes your work a heck of a lot easier. All right, have a great day.